Hi everyone, welcome to CS 188, Section 1 on search. So first we're going to talk about state spaces. So let's consider our running example of Pac-Man, which I drew here, a simple 2x2 grid with Pac-Man in the top left. So as the agent, we have kind of two questions that we're going to ask that state spaces will help us with. So question 1. So if I were the agent, what do I need to know to play? So what knowledge about the world do I need to know how to play the game? And 2 is how do I represent this knowledge? Represent 1. So these are kind of the two questions that we're going to be focusing on. Now, for state spaces, there's in general two separate components that we can talk about. So first, we can talk about the world state. What's part of the world state? In general, it's everything that stays constant. Okay, so for example, in this Pac-Man that I drew above, the map is constant. Although you could imagine a game where the map constantly changes, you need to map it, but in all of our examples in 188, the map will stay constant. Then we have the search state. And the search state is everything that changes, so the opposite of the world state. So some examples we have are Pac-Man's position, and another one would be the pellets, for example. You can think of many more, like the ghosts, where maybe if there's multiple Pac-Man on the board and things like that. So in general, this is what the world state and the search state are, and we're going to focus on the search state because that's what we need for planning and that's what we need to decide on. So again, let's consider our example of the 2x2 Pac-Man grid at the very top, and let me also draw in a green little pellet. So when you are presented with a state space question, you'll usually be asked, which we'll do on the worksheet next, is first, what do we need to track? What is the search state? So if we want, let's say the goal of the game is for Pac-Man to eat the pellet. Well, clearly we need to know where Pac-Man's position is. So the search state, SS, will be Pac-Man location, and as I said before, we probably also need to know where the pellets are in order to know how we're going to eat them as Pac-Man. So when you're thinking about these, you can view yourselves as the agent. What do I need to know to accomplish my goal? Now the second part, so this was number 1 in what I listed above. What do I need to know to play? Now for 2, how do we represent this? So for Pac-Man location, we're on a grid. So a common way would just to be the XY coordinate. Now if we go to pellet locations, we can also represent it as an XY coordinate. However, we also have some choice here. Since we know the map beforehand, we could also do Boolean variables. So if I draw the map here, and I have 2x2, I can have a 0 or 1 in each little grid. So that corresponds to 4 Booleans. So usually in number 1, it's you need to figure out what you need to know. But number two, you can have some leeway in how you represent them. So let me give you an example of when you might prefer either the coordinates or the Boolean when doing pellets. So let's say I have my 4x4 grid, or 2x2 grid, sorry, and I only have one pellet. That's just knowledge I know beforehand. It would be better to do XY because there's only one pellet. So you can imagine, well, if I make the board even bigger, the point gets across even more. So it's only one coordinate, but if I did Booleans, so I have one XY, but if I did Booleans, I'd have one, two, well, if I call this an M by N, so let me erase that. If I have an M by N grid, then if I need a Boolean for each position, because the pellet could be anywhere, so I need to be able to encode that, then I would have 2 to the mn would be the size of my state space. So that'd be for Boolean. And I guess I can call that, okay. Now, let's also say that pellets can be, that there's an m by n pellets. That's what we start out with. And the goal of the game will be to eat all of them. So I have all of this. Then having a bit, which is a Boolean for each one, will be a more efficient representation than having coordinates for tracking each of the pellets. So in this case, where they're all filled out, you maybe want to do Booleans. So that's the basics of state space. Okay, so now that we've defined our state space, we need to know how to plan through the state space, which brings us to tree search. So there are 3 key ideas in tree search. It's the ideas of a fringe, the expansion of nodes, or nodes or states, and an exploration strategy. I'll go into all of these in more detail. So as you saw in lecture, we can view this with this kind of high-level overview diagram where we have the start state S, and our tree goes down. And so we start at the start state, and we're going down, thinking ahead, where are we in the state space? And we're trying to get to a goal, and we don't know where the goal is. So at any point in our algorithm, which there will be multiple, we'll have some fringe, which is the line I just drew, which are all the nodes, which are, I'll use nodes and states interchangeably, which are all the nodes that we're currently considering. Then we have everything that's shading, which are all the states that I've previously visited. And then everything below are states that I have not visited, and the goal is somewhere down there. So for the running example, I'm going to go through, we'll consider a simple state space that looks like this. We have a start state, we have a goal state, we have a state I'll call A, a state I'll call B, and from the arrows will indicate where I can go from each state. So that'll be our running example, and I'm going to cover 3 different approaches or algorithms for doing tree search. So I'm going to cover DFS, depth first search, BFS, breadth first search, and UCS, which is uniform cost search. So I'll briefly go through each one, describe them, and then give the solution that would be for the state space graph. And then in the worksheet, we'll do some longer, harder examples. Okay, so for DFS, which stands for depth first search, you can think of this as going as deep as possible when you're doing tree search. So for example, we'll start at state S, and then we look at its neighbors, which are going to be A and B, and we always rate ties alphabetically. So then we'll go to A, and then we just keep going. So basically whatever path we're on, we just keep going until we can't go any farther. And then A, it can go to B or G. We break alphabetically, we go to B. We keep going as deep as possible. B can only go to G, and we'll be done. So I didn't write down the step-by-steps. I just went, this is a high-level view. And if you look at what it'll look like if I draw this diagram, what will the fringe look like, the nose we're considering? It'll look something like this. We'll start at the start state, and we'll go as deep as possible until we can't go anymore. So I'll have explored all of this, and we'll slowly go to the right. So that's what DFS will do. Now we'll go into BFS. So BFS, breadth first search, you can think of it as staying as shallow as possible. So if I look above, in this example, I'll start in state S, and then I'll look at the next level. So I'm going down by depth, where depth is defined as the distance to the start state. So then I'll be looking at the next level, and then there's no more nodes at that level. And then at the next level, if I do some work, then I'll see that SAG is what breadth first search will find. And you can check this by just looking at the graph, and you'll see, oh, if I just follow it, path 2, that's the quickest way I can get from S to G. And if you draw the little diagram we have above, it'll look something like this. So you'll be exploring, and your fringe will be roughly horizontal, which means everything has the same depth. And we'll have explored everything here. So that's what I mean by shallow. Okay, now we'll move on to uniform cost search. Let me erase. Okay, UCS. Now UCS is, at a high level, is stay as low cost as possible. Now, what do I mean by low cost? I've never mentioned cost before. Well, when you're doing UCS, the edges must have costs associated with them. So let me add some costs. So to go from S to B, it would cost 2 units. You could think of it as roads and tolls, whatever helps you think about it. 2, 1, I'll make this super expensive, 5, 3, and 1. So uniform cost search wants to find a path from S to G that's as cheap as possible. So if I look through it, I mean, it's so small that you can just find it on your own. So the algorithm would find S, B, G. And that'll have a cost of 3. In the worksheet, I'll go into detail about how to actually go through step by step, which will be useful in harder examples. So if I draw the diagram, this one will be less useful, less informative than the others. My fringe will look something like this. So I've explored everything shaded, and everything on the fringe will have a similar cost. And you can quantify similar, but I'm just going to talk at a high level. Okay, so that's the overview of tree search in DFS, BFS, and UCS. Let me erase this. I have a quick quiz question that you can think about. Okay, so here's a quick quiz. When will BFS equal UCS? So what do I mean by that? I mean, when will the solutions for what state graph? So can you draw a graph such that the solutions from BFS and UCS are always the same. So you can pause the video and I'm going to go over the answer right now. So BFS and UCS will be the same when all the edge costs are all equal. So this is pretty cool. When I go through the how to do DFS, BFS, and UCS, you can always, when they say do BFS, you can always just do UCS, but have, let's say, edge costs of 1, and that'll return the solution for BFS.